Hey there, it's Miss B, and in this video we are looking at the Unit 4 Lesson 10 Cumulative Practice Problems. This lesson was about domain and range, so let's dive in. This first question says, the cost for an upcoming field trip is $30 per student. So first of all, I'm seeing some information, I'm going to underline it. The cost of the field trip, C, so they're saying C represents the cost, and it's in dollars, is a function of the number of students, x. So if they're saying it's the function of something, I know that the number of students, that's my input. Because the output is a function of input, so my output is dollars and my input is students. So they want us to select all possible outputs defined by this function, and here is our function that we're looking at. So it's 30 times x. So if x is my input and my input is students, I can only use whole numbers for x because I can only have whole numbers of students. Everyone counts as a whole person. So that means 20 is not possible. But 30 is because, if one person went, that would be one person. It also means 50 is not possible, but 90 is, that's 30 times 3. And 100 is not possible because that doesn't work either. So this would be 30 times 1, and this one would be 30 times 3. And I'm going to put a little note here that says x is students. So the input is whole numbers only. Okay, so let's look at number 2. We have a rectangle that has an area of 24 square centimeters. Function f gives the length of the rectangle in centimeters when the width is w centimeters. So we have a width of w, that's going to be our input, and our output is the area. So determine if each value in centimeters is a possible input. So when we're talking about realistic and it has an area, the only thing that's going to prevent us from saying these are inputs is if we have negative numbers, because I can't have a negative width. And I also lied. I can also not use 0, because if it has 0, then we're going to multiply by 0, and our area is 0, and the rectangle just doesn't exist. So we can't have negatives, and we can't have zeros. But each of these could be answers, or they could be inputs. So as long as we multiply them by something, and they don't have to be whole numbers, we can multiply each of these by something to get 24. And if you're wondering, Miss B, but how do I multiply 48 by something and get 24? 48, if you multiply that by 1/2 or 0.5, that gives you 24. So we don't have to use whole numbers, we can multiply by fractions. Let's look at number 3. We're now going to select all the possible inputs and output pairs for the function y equals x to the third. So y is my output and x is my input, which means I'm going to take the values on the left, multiply them by themselves 3 times, because that's what x to the third means. It means x times x times x. So that would be -1 times -1 times -1. And in that case, yes, this one is true. -1 times -1 is +1, but then we multiply by -1 again, and we still get -1. The same thing is true with -2. If we take -2 and we multiply it by itself 3 times, we are going to get +8. Now, if we took 3 and multiplied it by itself 3 times, we actually get 27 and not 9, because 3 to the power of 3 is 3 times 3 times 3, which which is 27. So that's why we're going to say nope to answer C. And for part D, or option D, this one works as well, because with fractions, when we multiply, we're going to multiply straight across. So this would be 1/2 times 1/2 times 1/2, which means we would do 1 times 1 times 1 to get 1, and 2 times 2 times 2, which would give us 8. So this one works as an input and output pair. Okay, we have two more. Option E, 4 times 4 times 4. Yes, positive 4 times itself 3 times is 64. So this one works as well. And then for our last one, we have positive 1 as the input and negative 1 as the output. And this does not work because 1 times 1 times 1 will never give us a negative if the number itself isn't negative. So you should have A, B, D, and E for this. And so let's move on to the next page. We're going to look here at a small bus that is charging $3.50 per person for a ride from the train station to a concert. So I'm seeing $3.50 per person. That might be relevant. It cannot fit more than 10 people. So 10 people is the limit, and it will run if at least 3 people take it. So it has a lower limit and an upper limit. So function B is going to give us the amount of money when n number of people ride the bus. So we're going to identify all numbers that make sense as inputs and outputs. So since this is people, we are going to use whole numbers. So I'm just write myself that note here. Whole numbers. So we want also at least 3 and at most 10. Now, you don't have to write yourself those notes for this answer. You could just write the actual numbers. So that would be 3, 4, 5, 6, 7, 8, 9, and 10. Those are the only possible amounts. So this is really our answer, but I wanted to put those notes over to the side just to kind of explain how I got those. And so now we're going to sketch a graph of B. So at 3, we're going to plug 3 in to our equation. Well, we actually don't have an equation written here, but we need 3 people. So we're going to take 350 and multiply that by 3. And if you plug that into a calculator, I believe that gives you $10.50. So if we have 3 people, that's going to be right here down at the bottom in the middle of that 2 and the 4. And like I said, that should be $10.50. It's going to be right about here. Now our upper limit was 10. And if 10 people rode the bus, that would be 10 times 350, and that would be $35. So I can easily put my number here at 10 at 35, so that should be halfway between 30 and 40. And because this is charging a constant rate, I could just try to multiply out and see each number, or I know that I should have a constant slope, but I can't actually put information in for half numbers of people. So I'm not actually going to connect my graph because I don't have outputs at those values. So even though I could maybe take a shortcut and just connect my 2 dots here, I can't actually do that for this equation. So I'm going to take 4 and multiply it by 350. And that gives me 14, so 14 is a little less than 15, so we'll say it's like right there. And then if we take 5 times 350, that'll give us 17. 50, so we should be about, yeah, actually it's going to be right halfway between 50 and 20. 15 and 20, I feel like I said 50. So then if we have 6 people being charged 350, that'll be 21, right about here. 7 times 350 would be 2450. We're really just adding 350 each time, but 2450 is going to be almost 25, but not quite 25. 8 times 350 is going to be 28 on the nose, so right about here, I suppose. And then this one here should go right at there. 9 times 350 is 31.5. So maybe it's a little lower than this, but it's almost 32, so that seems in the right place. And if you look at all of my dots, they do make a linear pattern. So that is my approximation of this graph. If I want to be more specific, it can't really draw a straight line because you can't use fractions of people. Okay, let's do number 5. I have 2 functions defined by the equations f of x equals 5 minus 0.2x and g of x equals 0.2 times the quantity x plus 5. We're going to select all statements that are true about the functions. So this is going to be really just some plugging in information. Is the function value of 3 greater than 0? Well, yes. The function value of f for 3 is greater than 0 because I'm going to have 5 and subtracting 0.2 times that number. 0.2 times 3 is 0.6. So A would be correct. Now, is it going to be greater than 5? And since we're starting at 5 and then subtracting things from it, B is not correct. Because the most my function value could be, if I was using positive numbers like 3, is 5. And since I'm subtracting from it, it's just not going to be true. Now plugging in a negative number in option C here. So we're going to plug in -1, and that's plugging into G. So that would give us 4 on the inside of our parentheses, and then times that 0.2 would indeed give us 0.8, so C is also correct. Now, they're saying that the value of G at -1 is less than the value of F at -1, and I do know that's going to be true even without evaluating F because I know a negative times a negative is a positive, and if I'm plugging in here a negative number, that means I'm going to be having 5 plus something no matter what. So, and actually here, we're going to be having 5 plus 0.02, so it's 5.02. And so, yeah, if 0.8 is definitely less than 5.2. Okay. And last but not least, f of 0 is equal to g of 0. So when we plug in 0 to our first one, to f, we're actually going to get 5, because that's saying take 5 and subtract 0.2 times 0. Well, so take 5 and subtract nothing. And for g of x, we're actually just going to add nothing to the 5, because that's where we were adding our input. So this is not going to be true, because one of them is 5, and the other one is going to be 5 times 0.2. So not going to be correct. So just A, C, and D for this question. For question 6, we have the graph of a function passing through coordinate points 0, 3 and 4, 6. So we want to use function notation to write that information that it gives us about function f. So Well, what does it tell us about this function? Actually, is there more on here? No, it's just those two. Okay. So, first I know that the input of 0 gives an output of 3. Because they're not giving us any context, we're just going to say. Oh, wow. I totally misinterpreted this. It just says use function notation. It wants me to write this in function notation. I was thinking it was asking us to describe what each point tells us. Not the case. Wow, that was definitely a brain fart. So here we're actually going to say f of 0 is equal to 3. Oops. Is equal to 3. And f of 4 is equal to 6. And here I was literally going to write these as sentences in English. That's what you get if you don't read things closely. So learn from my silly mistakes. Read it closely. Use function notation. All right. So these are our two function notations for these points. Input goes inside the parentheses, and output goes across the other side of the equal sign. Okay, now let's keep going. Let's look at question 7 here. We have matching each feature of the graph, and then if it does not exist, choosing none. So let's look at what we have. They're asking us for maximum, minimum, vertical intercept, and horizontal intercept. Well, I see a maximum here, because that is the tallest point. So that's at 4, and it looks like the value is about 16. So 4 and 16, that's going to be my maximum. The minimum lowest point looks like it's right about here. So that is around 0.5, or I'm sorry, 1.5. Oh, yeah, and 2. So that actually works. That is this one right here. Okay, now our vertical intercept, that's where our graph would cross our vertical axis or touch our vertical axis. So that looks like that's going to be right here at 7. And so that's an input of 0 and an output of 7, or 0, 7, like this one right here. And then horizontal intercept is where this graph touches the horizontal axis, and it doesn't. So we're going to select none. There is no horizontal intercept on this graph. It does not touch the horizontal axis. Okay. And so I guess if we wanted to write these in the correct order, just because I always have a tendency to write the letters next to it, this would be C, B, A, and D. Okay. All right, this question is comparing some graphs in millions. So it's an audience of a TV show in millions. And so we're going to write that as a function of the episode number. So for each show, we're going to pick 2 episodes between which there is a negative rate of change if possible. So we're going to explain or show why it's not. Well, for show C, I definitely see a negative rate of change here. There's quite a few, but I'm going to use these 2 right here. So that looks like it's episode 5 and 6. So show C, episode 5. And in episode 5, they had like 5.5 million. And in episode 6, they had just shy of 4 million, so let's call that 3.8 I'm going to put a little wiggly line in front of it to mean approximately 3.8 million. But it's definitely below. Now for this one here, I actually do not see a place where there's a negative rate of change, because the only place that comes close is right here. Otherwise, the show has positive growth, and this is 0 rate of change. So show A is not possible. And we're going to say audience always increases or stays the same. Okay, so for show A, it's not possible because the audience always increases or stays the same. We literally cannot find a negative average rate of change. So, oh, the one part I didn't do, which they asked me to do, is estimate the average rate of change. I just kind of gave some numbers, but because this is a 1 episode gap from episode 5 to 6, that means that our episodes 5 minus 6 or 6 minus 5 is just going to be 1. So it's already sort of in our rate of change format. We're just going to look at 5.5 minus 3.8. So I want to say this is 1.7, but we can look at that on here, or I can just do some mental math. Let's actually just line it up. I don't even need to do mental math. I don't always trust myself with mental math. So 15 minus 8, that's where I was getting the 7 from, which means this 5 is going to become a 4, and then, yes, this is a 1.7. So, I actually put this in the wrong order. I should be doing 3.8 minus 5.5. Because I do want negative rate of change, and it's important that 6 and 3.8 should be in the same positions when we're subtracting. This is why I normally like to stack things up vertically, but I just chose not to for this one. And look at that, I made a mistake. So we're going to have negative 1.7 million. And so that is my estimate for the average rate of change. So you'll notice I didn't really estimate that the rate of change part. I actually did that subtraction. My estimate just comes from the millions I was estimating, so that 3.8 and the 5.5. And yeah, that is it. I had to double check, so that's why I peeked at my next page here, but that is it for this homework assignment. So this is Unit 4, Lesson 10, the Cumulative Practice Problems for Illustrative Math Algebra 1.